Okay, so now we can change variables. So we will set x equal to r cosine theta and y equal to r sine theta. And you should recall that dx dy will go to the Jacobian times by dr d theta. And you might know the Jacobian off by heart. If you don't, you should try to calculate it. It's good practice. But the Jacobian for this problem is just r. So we get r dr d theta. And of course, that makes perfect sense because dx is a length, dy is a length. So dx dy is length squared. Dr is a length, d theta is dimensionless. So dr d theta is a length, not a length squared. So the Jacobian has to be a length. And that means the only thing that it can be is r, because that's the only possible length that we have in our problem. Good. So now what does the integral become? Well, we have to evaluate the integral from 0 to 2 pi d theta. We have to evaluate the integral from 0 to infinity of dr. Then let's put the Jacobian in. So there's r. And then we've got e to the minus alpha over 2r squared. Well, the integral over theta is particularly trivial. We just get a factor of 2 pi. And then we've got the integral over r. And with a little bit of staring, you can see that the integral over r is also pretty easy. So let me just write down the answer. So it's minus 2 pi over alpha times by e to the minus alpha over 2r squared. So to check that, just take a derivative of this with respect to r and make sure that you get the previous line. And then, of course, we have to evaluate this between r is equal to infinity and r is equal to 0. Well, at infinity, the exponential goes to 0. So the answer is 0 at infinity. And at r is equal to 0, the exponential is just 1. So the value at infinity, 0 minus the value at r is equal to 0, minus 2 pi over alpha, is just 2 pi over alpha. So that's the answer. And what were we calculating here? I0 squared. So we immediately learn what I0 is. I0 is just 2 pi over alpha square rooted. And we can be pretty certain that we've done this calculation correctly, because remember, by dimensional analysis, we already argued that I0 had to be c over square root of alpha. All that this argument has done, it's allowed us to figure out what c is. And what is c? It's the square root of 2 pi. Great. So we've done one of the integrals when n is 0. But remember, we want to do all of these integrals in. So let me catch this, because I will want to discuss this below. So let's see if I can catch this. So we've done one integral. We still have an infinite number of other integrals to do. So let's take care of those now. Okay, so let me spell out the strategy that we're going to use. We're not going to calculate an infinite number of integrals. We're only going to calculate one integral. What integral will we evaluate? Well, we are going to evaluate I of b. And what I of b is, it's equal to an integral from minus infinity to plus infinity dx e to the minus alpha over 2 x squared plus bx. So that's the integral that we're going to evaluate. So first of all, I should motivate why are we going to do this integral? What's good about doing this integral? Okay, I want to remind you of two trivial formulas. If I take a derivative with respect to b of e to the bx, You know that the derivative of an exponential gives you the exponential back. Okay, the rate of change of an exponential is proportional to the exponential itself. But if we differentiate with respect to b, we know that we will bring down an x. So that's the first thing that I want you to keep in mind. And then, of course, it is a trivial step to take the nth derivative of e to the bx and to get x to the power of n times by e to the bx. Okay, so keep those two in mind. Now, I am going to imagine taking the derivative with respect to b of I of b. So look at this expression for I of b here. I can easily take the derivative into the integral because nothing depends on x. It's just a d by db. And then what am I differentiating? Just e to the minus alpha over 2 x squared plus bx. Okay? So there's no issue there. Now, as far as the derivative with respect to b goes, the minus alpha over 2x squared is neither here nor there. It just doesn't depend on b. So the only thing that we're going to be multiplying is the bx piece there. And then we can just use the formulas that I have shown you above. The integral from minus infinity to infinity dx of, now it's x multiplied by e to the minus alpha over 2 x squared plus bx. So I hope that that's clear. Make sure that you got that, because that's an important step. Now, I want to generalize this result slightly. Let's imagine that we took n derivatives with respect to b. So if we decided to do that, well, we can take all n derivatives inside, because again, nothing depends on b. And then nothing depends on x. So it's a d by db, we can take it inside the x integral. And then each time we differentiate with respect to b, we're going to bring down an x. So we're going to end up getting just x to the n. Now, compare what we've got on the side, okay? So compare what we've got sitting over here compared to what we've got sitting over here. And they look nearly exactly the same. The only difference is that if you look at the exponential, up in the exponent down below, we've got plus bx. So we just want to get rid of this bx term. That's the only difference between the expression in the box for in and the expression that we've gotten here. Okay, well, that's very easy to fix. So here's my claim. If we take n derivatives of I of b with respect to b, and then we set b is equal to 0, what is that equal to? Well, we need to take this expression that we've just written above, which is the integral from minus infinity to infinity dx. We'll have x to the n, and then we'll have e to the minus alpha over 2x squared. But this is nothing but in. And that was the important formula that I wanted to derive. So let's give it a red box. So instead of calculating an infinite number of integrals in, I'm going to calculate one integral I of b. So for this strategy to succeed, I'm going to need to show you that I actually can evaluate I of b. And what I'm going to argue, this is going to be important, I'm going to argue that I of b can be calculated knowing nothing more than I of naught. So the calculation of I of b is no more difficult than the calculation of I of naught. So that in actual fact, at the end of the day, we would have calculated this infinite number of integrals in using only the result for I naught. And we're going to generalize this strategy when we study path integrals. We'll have to perform a single path integral. And when we know the value of that one path integral, we'll be able to evaluate any correlation function. And it turns out that we're actually going to be able to implement that strategy. And that's going to be how we land up evaluating the path integral.